The sound from two different speakers can sometimes weirdly sound hollow or suddenly quiet. This is because the sound waves literally cancel themselves out when the conditions are right. So let me explain something to you. Sound cancels depending on position. And what this would look like, this. You got one speaker, and you got a second speaker. And this is you. This is where you are. Sound waves come straight to you. And if they're at an equal distance, then they arrive in phase, equal distance. So the type of interference from them entering the same space is constructive interference, which I talked about in my interference video. This means that the two crests, aka the two peaks, collide, and they add up to one taller crest. Same with the dips. The sound is perfect and it's loud, so everything's all good. But what if you were not an equal distance away from these sound speakers? You got your same speakers, but this time you're standing here. The distances are no longer equal. One speaker sending sound waves like this and one sending them like that. They arrive out of phase. And if the path difference is correct, so the difference in pathing distance, if it's just right, then the sound will be zero. There will be no sound because perfectly all of the crests will cancel with all of the dips, creating a net zero, flat. Usually that's pretty rare. Usually it will just make the sound worse and quieter because the interference is called destructive interference. So that's when points of compression meets points of rarefaction, high pressure, low pressure. They will cancel and it won't sound better. Here are the conditions for interference when it comes to situations like this. For constructive interference is path difference equals n times wavelength. And what's this path difference? It's R2 minus R1, with R2 being the distance from one speaker to you, and R1 being the difference from the other speaker. So that's for constructive interference, which makes it louder. How about for destructive interference? The path difference is found with this new formula, n plus 1 over 2 times wavelength, with n being 0, 1, 2, and so on. This will make sense if we go through an example. Imagine that you have two speakers, speaker 1, speaker 2, and they are 1 meter apart. You are standing here, 2.5 meters away from this left side speaker. How far do you have to be from the right side speaker for the sound from both speakers to cancel out? Assuming that the frequency is 1150 Hz and the speed of sound through air is 343 meters per second. All the formulas you'll need are on the free cheat sheet in the description and every formula for this topic that we've covered in this video. First, we have to find the wavelength, because the path difference formula involves the wavelength. Wavelength is found with the standard formula velocity over frequency, 343 over 1150, roughly 0.298 meters. Now, for the path difference, we want the wavelength to be divided by 2 perfectly. This means that they arrive perfectly out of sync with the crests meeting the troughs, giving us a flat zero, aka silence. That is 0.298, like we just found, divided by 2, which is 0.149 meters. What does this number mean for us? It doesn't mean that this distance is 1.49. No, it means that this distance must be 0.149 more or less than our other speaker distance. So either 2.65 meters or 2.35 meters. Now, what are beats? Beats are interference in time. So when two sounds are close in frequency, they phase in and out over time. What does that look like? I'll show you. It's cool. This is our graph. We have our first wave moving like that at this specific frequency. And our second wave is close in frequency, but it's just slightly different. It's just a little bit off. So over time, they phase in and they phase out. And when you add up these waves, when you add up the height at each point, like you do with waves, the result is something like this. See, they're louder because they're combining properly at points. Sometimes they're just not right at all. So the volume goes loud, quiet, loud, and this is called a beat. You're hearing a pulse in amplitude caused by a small frequency mismatch. And the formula for this, which is also on the cheat sheet, is F beat. So the frequency of this beat is equal to the absolute value of the frequency of the first wave minus the frequency of the second wave. Let's go through an example so we can make some sense of this. This concept is quite satisfying as well. So have you ever seen a tuning fork? What you do with these is that you hit them, you tap them on something like your knee, and they make a super laser beam sound at a very specific frequency. And you can compare it to a sound of, let's say, an instrument like a guitar to see if your guitar is tuned. So you hit your tuning fork and it rings at 400 hertz. You also plucked your guitar string at the same time. And you listen to these at the same time. And the beats you hear, so the amount of mismatches you hear in frequencies, 20 beats over the course of 5 seconds. Beats are sound pulses in and out when almost the same frequency is happening. The amount of times that these beats happen tells you how far apart the frequencies are of our two objects. That tells us how close our guitar is to being in tune. The fork is at 400 hertz and you heard 5 beats in 4 seconds, which means that, and you heard 20 beats over the course of 5 seconds, which means that per second you would hear 4 beats. That means the frequencies are 4 hertz apart, 4 cycles per second apart. So the guitar is either 404 hertz or 396 hertz. It's 4 hertz apart from your tuning fork. That's where the beats are coming from. If they were perfectly matched, you wouldn't hear any. This makes studying 10 times easier. Go download the free cheat sheet in the description and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.